All right, in this video, we're just going to collect a quick corollary of the previous example that we did in the previous video, and then a quick lemma, um, and then the next video, which should be the last one, we're going to look at extending homomorphisms. So, corollary: suppose k alpha over k and k beta, k join beta over k are simple algebraic extensions, such that alpha and beta have the same minimal polynomial m. Over k. Then k alpha is isomorphic to k beta, and the isomorphism can be chosen to be the identity on k. All right, cool. So we saw this already, right? In a previous example, we had two different cube roots of 2, one real, one complex. We saw that by adjoining either of them, we get isomorphic extensions, and this was just evaluate, so it didn't change any of the coefficients. Really, if you wanted to describe this function, it's replace alpha with beta, right? That's what that function is. And if you look back to homework 1, when you did this problem, or with omega alpha rather, replace alpha with omega alpha. If you look back to homework 1, when you did this problem, all you did for that function is you replaced alpha with omega alpha, right? So this is going to be very similar, so let's prove it. Proof. Suppose again that alpha and beta have the same, min poly over k, and then what? Well, by the theorem, there's two isomorphisms. There's one which evaluates t at beta, and there's another which evaluates t at alpha. Oops, let me give myself a little more space there. Both of these are isomorphisms, and if we want to construct an isomorphism from the left to the right, we would go by first undoing the first map and then following it with the second. Okay. By theorem, blah, 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 and evaluation t equals alpha, evaluation t equals beta are isomorphisms. Thus, the function phi from k alpha to k beta defined by, well, we're first going to undo evaluating at alpha, and then we're going to evaluate at beta. This is an isomorphism, being the composite of isomorphisms. All right, great. That does it. And I guess also, since, let me say it this way, evaluation t equals alpha, evaluation t equals beta, both fix k, because we're just plugging in a value for t, so does phi. So it's the identity on k. That's it. All right, again, very, very helpful. Know how to work through an example of something like this, like we did in the previous video. Very, very helpful. Lemma, let k alpha over k be a simple extension, simple algebraic extension rather. Okay, so again, this means that alpha is 0 of a monic polynomial over k, so we can say m alpha, let m alpha be the minimal polynomial that exists. and suppose that the degree of the minimal polynomial is n. Then 1 alpha alpha squared alpha to the n minus 1 is a k-basis for k join alpha. We'll get more into the vector space theoretic properties of these extensions. So linear algebra is going to enter the picture in the next chapter. But for now, we can make this observation. This is an incredibly helpful observation as well. It seems silly, but it's not. So proof, let's see, by one of our theorems, well, let me just say it this way. We proved a theorem where we saw that every element of k adjoin t mod m alpha has a unique representation let me say every element, let's be more precise, a bar of t has unique representation such that the degree of a bar is less than the degree of m alpha. Okay, so that, and this is n by in the problem. Oops, m alpha. That was just the remainder, the division algorithm, right? We said, okay, what do elements here look like? Well, I divide a by m alpha, I get some remainder, and the division algorithm told me that that is unique, that there is one and only one way to do that. Right? So it has a representation like this. So we can express uniquely a bar as some a0 plus a1t plus a1 t to the n minus 1. It has to be n minus 1 because it's degree less than n. Always degree less than n. There's n terms here though, so keep that in mind. So not a1, a n minus 1. My bad. All right. Now the field k adjoin t mod m alpha is isomorphic to k of alpha via evaluate t at alpha. And this, again, isomorphism need not be unique. There could be many of them, but this is one such isomorphism. Thus, any element of k alpha comes from one of these unique representations here, and since it's an isomorphism, it comes from the unique representation uniquely. So any element of k adjoin alpha is uniquely represented as, well, I just evaluate a general term on the left, right? And if we evaluate on the right, the function plugs in alpha. So we're going to take this and we're going to plug in alpha everywhere. And then let me just write one thing. This a0 is really a0 times 1. Right? So we have a unique representation where the a0 through an minus 1 rather are in k. I didn't specify my variables up there. Sorry. Okay, so this is unique. What does it mean to be a basis? It means that every element in that space has a unique, can be represented uniquely as a linear combination of elements in your set. Okay. That's the unique is the one word way of saying spans and is linearly independent. Okay. Okay, so what are the elements that things in my field are k-linear combinations of? They're combinations of 1, alpha, and so on, all the way up to alpha n minus 1. So thus, 1, alpha, continue taking powers is a k-basis. All right, that's the end. I know it can be a little bit confusing when there's not a hard example to put, sink our teeth into. So let's go back to that cube root of 2 example. So P plus Q alpha plus R alpha squared, and then PQR and Q, and alpha is a real cube root of 2. All right. So in that case, we stopped at alpha squared, right? Why did we stop at alpha squared? Well, we stopped here because the minimal polynomial of the cube root of 2 is t cubed minus 2. It's degree 1 less. We have to stop at degree 1 less. Why? Well, when we hit that degree, when we raise alpha to the third power, the minimal polynomial tells us sort of that it wraps back around. So we don't actually need the cubic power because it will wrap back around. Okay. All right. So what do we learn here? Well, we learned that one. Let's even really write out the cube root of what alpha is. It's the cube root of 2 and the cube root of 4. This is a Q basis for Q adjoint alpha over Q as a Q vector space. Okay. All right, so that's a very specific example where we can sink our teeth into what's happening. And the lemma says that that specific example happens in general.